So we've now looked at how you make the Born-Haber cycle for an ionic compound. Just to recap that, remember, the Born-Haber cycle is just showing a number of steps for you to get from a solid ionic lattice to the separate gaseous ions via an alternative route. Now that changes the Lattice enthalpy. That's what we're trying to calculate in this topic. It's quite a useful value for us to get, but we can't get it through an experiment. We have to do it via this kind of other method where we use a combination of lots of different experimental values with a wee bit of maths to work out what this value is. So we formed our cycle, but now we need to look at how you actually use that with numbers. Now the one thing to reassure you at this point is if you've done all the hard work and if you understand the Born-Haber cycle you've got in front of you, the maths behind this is actually very simple. It's basically adding numbers together. It's nothing more complicated than that. So what you'll be given in the question, again, you'll see when you actually look at past paper questions yourselves, they might give you a partially completed Born-Haber cycle, they might give you a fully completed one, they might give you no Born-Haber cycle, but you have to get to the point where you've got a Born-Haber cycle in front of you. What they'll then give you is a table most likely, and the table will have a number of enthalpy change values given to you. Now you notice that the Lattice enthalpy probably won't be given to you in this particular example. That's the one you're trying to calculate. What I have given you here is the values just in this table for the enthalpy of formation of sodium chloride, atomization of sodium, first ionization energy of sodium, atomization of chlorine, and first electron affinity of chlorine. So what I said was if you've done your Born-Haber cycle correctly, it should just be a simple case of transferring these values onto the appropriate position on your Born-Haber cycle, and that'll make the maths a bit more clear cut for what you have to do. So as we go doing that, I'm going to do it up here, so you don't have to mess your notes up, but I'll just show you on this diagram. First value I'm given in the table is formation of sodium chloride is minus 411. The enthalpy of formation is this one, so I'm just going to write on it minus 411. Atomization energy of sodium, that's this change here, is given as plus 108. Again, I probably should be putting units down, but just to make it clear, I'm going to put the numbers down. First ionization energy of sodium is this change here, it's plus 500. Atomization energy of chlorine, that's always the one I want you to be careful about because they could give you the value for bond association enthalpy, you might have to change it. But just to check, in this change here, I'm forming one atom of chlorine, therefore it must be atomization values. So them giving me the atomization value is the correct one, I don't need to change it in any way. So I can just write down it's plus 121 for that value. Almost there. The electron affinity of chlorine is given as minus 364. Notice it has a minus sign because it's exothermic. That's why our arrow is pointing down. So now we've got our numbers transferred onto our Born-Haber cycle. Now we're going to go back to using it a bit like a Hess cycle question or Hess's law question. The change I want to calculate is this one here that I don't know, the Lattice enthalpy. I've got a number of other changes which could give me an alternative route around that cycle. And remember, Hess's law states that it doesn't matter what route you take, the number at the end should end up being the same. Just the difference is I've got a number of different steps to include in that now. Now, I do have to be careful in one sort of thing for a start. I need to make sure I'm following arrows. Remember, if I'm following arrows around the cycle, I just add the numbers together. Though if the arrow's pointing the wrong way, I have to fix that before I do that. Most of the arrows actually are correct. So remember, I have to go from NaCl solid to Na plus and Cl minus. Just be in that direction. So I need an alternative route going from the bottom to the top, which is basically going to be curving around this route here. So note that on. Now, in actual fact, most of those arrows are actually pointing the correct way. This pointing up, this pointing up, this pointing up. This needs to point down. This brings us back towards the final resting point of this cycle. There's only actually one arrow which isn't pointing the correct way, and hopefully spot it's the delta H of formation. It's pointing down, but needs to be pointing up. Again, that doesn't bother us too much. We just need to flip the arrow in our cycle, and if we flip our arrow, we have to change the sign. The number I'll therefore use in the sum is plus 411. What you should see on the next page of your notes is actually the completed version of the diagram. The bit at the top just goes through and explains what I've just told you there. You can read that yourself. And these are the numbers transferred on. Again, you see in bold here that arrow, that's the one that's being flipped. The formation value is minus 411, but we flipped it to make it work for our route around this cycle. So now we're finally at the stage where we can just do our calculation. And once you've got your arrows set up around your cycle, it is just a case of adding your values. So to work out this lattice enthalpy, I'll do plus 411, plus 108, plus 500, plus 121, plus minus 364. I can put that in brackets to make it clearer for myself. Second, the calculator comes out as being plus 776 kilojoules per mole. Remember, I have to put a sign there if it's a plus or minus and give my units as well. So that is your kind of basic or standard Born-Haber cycle question. You construct the cycle, it gives you some values to put onto your cycle. You have to manipulate the arrows a wee bit and then follow your cycle around, adding numbers together to work out what the missing lattice enthalpy value is. They can obviously do wee variations in that with calculation. In some questions, it might actually give you the lattice enthalpy, and maybe one of these values is missing, and you have to do a wee bit of manipulation to work back to work out what the missing value is. But you'll see that as you approach some of the past paper questions. Now, it's not the only type of Born-Haber cycle we'll come across. As you even see, next wee subheading, there's a couple of variations for different types of ionic compounds we'll look at. But I think at this point, before we go too far, there are a few past papers I've uploaded you can have a go at. In the document, you, at this point, I think, can attempt pretty fairly questions 1 to 6. And I'll give you an idea of the basic kind of normal style of Born-Haber cycle question. And then when you come back, we'll look at maybe some of the harder or different types of cycle you can get.